The Reductionist Delusion. Is life really a game of pinball? In a lecture at the University of Scranton in 2009, Murray Gell-Mann endorsed a typical version of reductionism. Everything comes down to the laws of physics, the initial conditions, and chance. In this view, economics, for example, is really only psychology. Psychology is really only biology. Biology is really only chemistry. Chemistry is really only physics, and physics is ultimately only whatever happens with fundamental particles and fields. This is why the view is called reductionism. Everything gets reduced down to fundamental particle physics, initial conditions, and chance. The argument we give later on hinges a lot on chance, because we can neutralize the role of the laws of physics and the initial conditions in regard to our argument. So let's turn our attention to the aspect of chance. First, we need to realize that the appeal to chance can be good. It enables us to get the gist of what is going on so that the rest can be regarded as noise. Probability and statistics can help us make a best guess instead of just any guess. Probability and statistics are very important in many real-life applications. For example, experimental sciences. Actuarial science, which has to do with future contingencies such as accidents, death, disability, and how long and whether a series of payments will continue, heavily employs probability and statistics. These are naturally very important in regard to investments, insurance, pensions, and so forth. These, in turn, greatly affect policymaking at the individual and societal levels. So, it is a good thing that statistical methods and the appeal to chance have been developed as much as they have, and the reliability of these methods allows scientists to make predictions, companies to stay in business, and people, in some way, to make provision for the future. So, in regard to the present topic, if you don't accept the argument I'm going to make, then you will have to throw out a lot of science and experience confirmed daily, because we are appealing to very basic statistical arguments and tools that scientists use all the time. Now that we have looked at some of the benefits of using statistics, we should have a look at some caveats in regard to what Gell-Mann said. Number 1. Gell-Mann's view, as he has stated it, undermines science. Over-reliance on chance undermines the appeal to scientific laws. How so? Because experimental evidence that is put forward as supporting a scientific claim can be dismissed as a mere chance outcome instead of evidence for that law. If I run Galileo's experiment on the law of falling bodies and find, as he did, that the distance traveled is quadratic in time, a skeptic could say, well, it looks that way, but that is just a fluke. Your experiment is just a chance outcome, not a corroboration of your claim. Over-reliance on chance undermines appeal to scientific laws. Caveat 2. Gell-Mann's view undermines rationality. It undermines the appeal to reason. If what Gell-Mann says is true, then reason is futile. How so? Does Gell-Mann say, "Thank chance I'm not a creationist"? Does he say, "Thank the laws of physics and the initial conditions that I am not a creationist"? If his view explains everything, including his own thoughts, then he is trapped, and so are we. He cannot claim to be more rational than we are in his views, because his views would be only the result of physics, the initial conditions, and chance. There would not be any way to convince others by appealing to proof and argument, or at least there would not be any reason to give this more weight than any other mental trajectory controlled by physics, chance, and initial conditions. Caveat 3. Gell-Mann's view undermines humanness. It undermines the reality and distinctiveness of personal acts. How so? If laws, chance, and the initial conditions are the whole story, then human initiative, choice, and responsibility are illusions. Get the bumper sticker. Dawkins happens. See what I mean? When an author, such as Richard Dawkins, asserts a copyright, which he does, he asserts both that the work is his and that it is not someone else's. Someone who plagiarized Dawkins would be guilty of copyright infringement. Would he get away with claiming the duplication was merely the result of chance? A copyright is an assertion of personal responsibility. On to the argument. A probability distribution tells how likely an event is to occur. With the uniform distribution, all the events are equally likely. Classic textbook cases of a uniform distribution are a fair coin which is equally likely to come up heads or tails, and a fair die which is equally likely to come up any of the faces 1 through 6. The normal distribution is extremely well known with its bell-shaped curve. It arises so much in theory and in applications that it is one of the most important statistical distributions of all. The Poisson distribution is a counting distribution for relatively rare events. For example, it could be used to model the distribution of the number of fish caught in a day. There are many, many others. Distributions are distinct in general. Statisticians look at a number of properties a given distribution has or does not have. For example, whether a distribution is symmetric or not. The normal distribution is symmetric, but the Poisson is not, so they are distinct distributions. Even so, sometimes a special case of one distribution will be equivalent to a special case of another. There are sophisticated statistical tests and techniques to tell when two distributions are different. For example, the Kolmogorov-Smirnov test. Now, another concept. A permutation is an arrangement of an ordered set. For example, 4, 2, 1, 3 is an arrangement of 1, 2, 3, 4. 1, 2, 3, 4 is an arrangement of 4, 2, 1, 3. And for very good mathematical reasons, we can say that 1, 2, 3, 4 is an arrangement of 1, 2, 3, 4. There is an unbelievably rich, deep, and vast theory connected with permutations, but that is a digression we have to resist here. Question: how many permutations does a set of n elements have? Answer: n factorial. A set of 2 elements can be arranged in 2 ways, 1, 2, and 2, 1. A set of 3 elements can be arranged in 6 ways, 1, 2, 3, 1, 3, 2, 3, 1, 2, 2, 1, 3, 2, 3, 1, 3, 2, 1. You may have noticed that we just inserted the number 3 into the 2 permutations for 1, 2 into positions that work, giving 6 results. If you now insert the number 4 into each of these 6 lists, you get 24 lists in all. As you can see, factorials grow even more rapidly than the national debt. One property that a permutation can have but does not have to have is one or more fixed points. For example, 5, 3, 2, 4, 1 keeps 4 in place even though the other numbers are moved. 2, 4, 5, 3, 1 does not have any of the numbers in the same places relative to the order 1, 2, 3, 4, 5. Every number has been moved. A permutation in which every element is moved is called a derangement. Question: what proportion of permutations have no fixed points? That is, where every number is moved. When we look at all the possible permutations, what percentage of them are derangements? Answer: if the set has 8 or more elements, the answer is basically 1 over E, where E is Euler's constant, 2.7182818. In other words, about 36.8% of permutations leave no member fixed. They are derangements. Example 1. The game of Iran-Contra. 2 players each have shuffled 52 card decks. Player 1 turns over a card, then player 2 turns over a card. If, at any point, the cards match, then player 2 wins. Otherwise, player 1 wins. Is this a fair game? No. There is a 1 over E equals 36.8% chance of no match. You can regard deck 2 as a permutation of deck 1. Player 1 has only a 36.8% chance of winning instead of 50%. They could perhaps flip a coin to see who goes first in a round, but whoever goes first in a round is automatically at a disadvantage. Or you could make the game fair by stacking the deck every time to make the winning odds come out to be 50-50. Example 2. Valet parking. A valet parks each person's car. When he fetches the cars later, how often does everyone get the wrong car back? Chance says that about 36.8% of the time, nobody would get the right car back. No one at all. But in real life, this isn't the case. So, the laws of physics, the initial conditions, and chance cannot explain what happens in real life. Some cause not reducible to these 3 must be at work here. Example 3. Quiz 1. Here are the correct answers. How many did you get correct? Average score of 1 for people taking this quiz, right? That is what chance predicts. If x is the number of fixed points of a random permutation, then the mean and standard deviation are 1. It's obvious, I hope, that we would still get the same results with any variation of the test, listing the questions and answers in any order. If you want to be really formal, you could use design of experiments to do this. The point is that we can zero out the effect of the laws of physics and the initial conditions by giving every possible variation of this test. But the scores will still turn out the same, we have no doubt. So we can focus on the aspect of chance. Here is another quiz for you. What is your score now? The overall average score of people taking this quiz will be 1 unless they actually know the people being referred to. Nearly 75% of people will score a 0 or a 1 on this quiz. In this instance, those named in the quiz are old friends of the quizmaker, and so he knows the right answers. Okay, one more quiz. Rank the towns. We can't know what the answers are unless we know how we are supposed to order them. Are these towns to be ranked by age, population, area, or something else? Income, educational level, vital statistics, etc.? In fact, there are infinitely many different criteria that could be used to determine the ranking, and 720 different rankings could result. The point is that there is not some hidden, tacit necessity that brings out the right results, because the right results sought depend on what the rule for ordering is. The rule for ordering the data is not intrinsic to the data, so the correct order does not simply fall out from physical necessity or the initial conditions. We also see that it does not fall out from chance. There must be something beyond physical law, initial conditions, and chance to bring about the correct order. The distribution of correct answers follows chance if you do not know them. It does not follow chance if you do know them. And the distributions are different, which you could verify by using standard techniques. Typical quiz results in real life for a typical class look like this: a somewhat bell-shaped distribution that should center over a middle C grade. This sort of distribution, I imagine, is quite familiar to anyone involved in testing. Quiz results according to chance. This distribution is not the same as the real-life observed distribution, so chance cannot be the full explanation. Other similar situations to what we have been talking about: assigned seating versus open seating, filling orders so that each customer gets the right order, deliveries, sorting. Even when we automate these tasks, it is because we build machines and program computers so that we know what we are after, even though the machines and computers do not. You could even look at multi-stage situations. Processing mail ordinarily involves several stages which could lead to total disorder. Instead, because ordering intelligence surpasses the capabilities of physics, chance, and initial conditions, mail can be put into the correct envelope and delivered to the right mailbox. Received mail can be sorted by any number of criteria, such as date received, sender's name, etc., and then responses can likewise be correctly sealed and delivered. Intelligence is not reducible to the laws of physics, chance, and initial conditions even when all these are taken together. It yields observable phenomena they cannot explain. Sapientis est ordinare. It is a mark of intelligence, a trademark of intelligence, to put things in order.